Hey guys, in this video we're going to talk about Chapter 8, Section 4, Density and Center of Mass. So we're going to be looking at how to use integrals with physics applications. So the first thing is, intuitively, what is density? Density is basically how much stuff something has in it, right? So it's the mass per unit of measurement. So I guess one way to think about it is like, if you have a crumpled up piece of paper, that's the size, and then you have an apple that's the same size. Well, the apple is going to be more dense because it is heavier with respect to the size, right? So these are both the same size, but the apple is more dense. One really cool object is that I like to think of when I think about a very dense object is what's called a white dwarf. Some of you guys may have heard of it, but basically it's a collapsed star that is very, very, very dense. And to think about it, how dense this thing really is, if you have a white dwarf that's the size of the Earth, okay, so looking at this picture, we have a white dwarf the size of the Earth. The mass of that white dwarf is the same as the mass of the sun, okay? So all of that mass is packed in this little itty bitty dot. So white dwarf, very dense object, very cool thing to study, if you're interested in astronomy. So density. Okay. So let's talk about density in terms of units of measurement. Okay. So we have three different cases. Now, the cases that I just talked about with the apple and the crumpled up piece of paper, those are three-dimensional objects, right? That's mass per volume. But we can also talk about one-dimensional density, and density in this case, in the one-dimensional case, is mass per unit of length. So in that instance, we could have something like kilograms per centimeter or perhaps pound per inch. In the two-dimensional case, bumping it up a dimension, instead of mass per length, now we have mass per area. So units of mass per unit of area, and so some examples of that would be kilogram per centimeter squared or pound per inch squared. And finally, the case that we just talked about with the white dwarf and the apple and the crumpled up piece of paper is the 3D case. That's what we usually think of with density, mass per unit of volume. So some examples, we have kilogram per centimeter cubed or pound per inch cubed. So, okay. So let's just get into it. How can we find the mass of a one-dimensional object? Okay. So for these problems, we want to assume that these objects, even though when you think about objects like wires and rods, you're thinking about three-dimensional objects, but we want to treat these objects as if they're just a straight line, that they don't have any kind of thickness at all. Okay, so it says find the mass of a wire that is 10 feet long, starting at x equals 0, and has a density of, so we call this delta. Delta x is equal to x squared plus 3x grams per foot. And these units, that's a key indication that we're in the one-dimensional case because we have units of mass per units of measurement. All right, so how do we go about doing this? Well, we just said the density of a one-dimensional object is going to be the units of mass over the units of length. Okay? So if we want to find the mass, all we have to do is multiply both sides of this equation by L to get that the mass is equal to the density times the length, right? So the way that we can do this, so we're imagining that we have this wire that's 10 feet long. Okay, so we're starting here at 0 and we're going to 10. And so maybe we have this thing right here, this wire with no thickness. And the density of the wire is varying because it's a function. So for instance, at x equals 0, the density is 0, right? Not dense. When x equals 1, if we plug in 1 into the density function, we get that the density is 4, right? So the density is varying, right? And because of this, we need an integral to figure this out, right? Right? So the idea here is that we're going to start at 0 and we're going to add up all of the little masses all the way until we get to x equals 10, okay? So the way that we're going to do this is we're starting at x equals 0, we're going to x equals 10, and the mass is going to be the density function, right? Density function. So this is going to be x squared plus 3 times the length. Or was that? No, I'm sorry, that was 3x. I got erased. Times the length. Well, remember, when we're doing integration, we're looking at the length of these tiny little rectangles, this dx value. Okay, so that is going to be my dx. Okay, so here we have our density times our length. And so we're going to sum up all of these little masses from 0 to 10. So let's go ahead and do that. Let's go ahead and integrate this thing. This is a pretty simple integral to work with. Okay, so if we find the antiderivative of x squared plus 3x, we get x to the 3 over 3 plus 3x squared over 2. And we're going from x equals 2 to x equals 10. And if I plug in 10 in for x, I get 10 cubed over 3 plus 3 times 10 squared over 2. And of course, if I plug in 0 in for x, all of this expression goes to 0. So that's nice. So what I'm going to get here when I do the computation is I'm going to get about 183.3 grams, right? That's my unit, because what did I just find? I just found the mass, right? Remember this equation. Density is equal to mass over length in the one-dimensional case. I solve for mass by multiplying both sides by length, but I have to, because the density is varying, I can't just plug and chug here. I have to set up an integral starting at x equals 0 all the way to x equals 10 and add up all of those tiny masses to get the entire mass of that one-dimensional thing. So I end up getting 183.3 grams. Let's do another example, and I encourage you guys to try this. So again, when you see in your homework rod, they're meaning a one-dimensional shape. So you don't want to think of a typical three-dimensional rod. You want to think of this thing as having no height, basically. One-dimensional object. So again, density is mass over length in the one-dimensional case. And so we need to set up an integral again to find the total mass. Now, the density function here is 2.1 plus 2.1x to the third. And this rod is positioned on the x-axis. Let me draw this out a little bit better. So it's 4 meters long, and it's starting at x equals 0 all the way to x equals 4. So we have this this rod that we want to think of just as like a one-dimensional line. All right, so there's our rod. And even though it looks like the density is constant because I drew it like a straight line, this thing is telling us that it's not. It's telling us that when x equals 0, density is 2.1 grams per meter. And then it starts increasing all the way to x equals 4. So the density is changing as x changes. So we need to set up an integral to, to find the total mass of this thing. So where are we starting? We're starting at x equals 0, as we can see here, and we're ending at x equals 4. And again, if we rearrange this formula, the mass of this one-dimensional object is the density, which is 2.1 plus 2.1 x to the third, times the little dx, the length of the rectangle. So this is density times length equals mass. All right. So let's go ahead and integrate this thing. Again, this isn't too hard to do. If I find the antiderivative, I get 2.1x plus 2.1 x to the 4 over 4. And I'm going from 0 to 4. So I get 2.1 times 4 plus 2.1 times 4 to the 4th over 4. And again, when we apply the fundamental theorem of calculus, we end up getting minus 0 when we plug in 0 for x. So just leave it like this. And then punching this in the calculator, I'm getting 142.8 grams. This is my mass of the object. All right, so let's bump it up a dimension. Let's look at the mass of a two-dimensional object. So it says, suppose a lamina. Okay, so a lamina is just, you can just think of as like a very, very thin plate. So it technically has some thickness, but we don't consider it for this purpose. So we're considering it as a two-dimensional object. And the shape of the lamina is a region between the graph of y equals x to the 3, y equals 0, x equals 0, and x equals 2. And then suppose the lamina has density of delta x equals 2x grams per centimeter squared. What is the mass of the lamina? Okay, so let's go ahead and just sketch out what this region looks like, this lamina. So we have, it's bounded by the x and the y-axis, right? And x equals 2. So let's just draw that here. And it's also bounded by the curve y equals x to the 3. So starting at 0, if I plug in 0 into that y equals x to the 3, I get 0. If I plug in 1, I get 1. And then if I plug in 2, I get 8 all the way up here. Okay, so maybe it looks something like this. It's probably not going to be as straight, but maybe I'll make it a little curvier. Okay, so that's the idea. So this is our region right here. This is our lamina. And we have a density function. So in the two-dimensional case, remember what we had? We had that the density was equal to the mass over the area this time, right? Now the mass in this case, if I multiply both sides by A, the mass is going to be the density times the area, right? So again, the area of this region, well, we've done that plenty of times before finding the area under curves. It's just the sum of these little rectangles, right? All the way from our starting x value to our ending x value. That's what the area is. So, so let's set up our integral. So where are we starting and where are we ending? Well, we're starting right here. That's where my region starts. And that's going to be at x equals 0. And then I'm ending right here at x equals 2. That's where my region ends. And I want to take, again, I'm trying to find all the little masses. I'm trying to sum up all the little masses. So I take the density function, which is 2x, which we're given up here. Density times the area. So again, this part is our density times the area. What's the area under this curve? Well, the area, again, think about the rectangles, right? The length is going to be dx, and the height of this rectangle is just going to be x to the 3, right? The function. So this is our y equals x to the 3. So the area here is going to be x to the 3 dx, right? Length times width. So this is our area. Density times area equals mass. Let's go ahead and figure out what this is. Okay, so first of all, I can pull out that 2 in the front. And I end up getting x to the 4th dx, which is easy to integrate. This just becomes 2 times x to the 5 over 5 from 0 to 2. And if I plug in 2 in here, I get 2 times 32 over 5. And of course, when we plug in, minus 0 to the 5th over 5, it just goes to 0. So our answer here is going to be 64 over 5. Remember what we just found? We just found a mass. So the units of our mass we are given in grams. So this is grams. All right, let's do another example here. We have a plate with constant density of 2 grams per centimeter squared is in a shape bounded by the curves y equals x squared and y equals the square root of x. With x and y in centimeters, we want to find the total mass of the plate. So again, we're considering this plate to we can basically neglect the thickness because it's so small, okay? So that's what they mean by plate, lamina, just 2D objects. Now they tell us that the density is constant. So whatever our plate looks like, the density is completely constant throughout the region. If you were to take a pencil and put it, basically like balance this plate, it would stay balanced right in the middle because the density is uniform throughout. So, with that being said, let's set up our problem. First of all, I'm going to sketch the region. Now, we have a shape bounded by the curves y equals x squared and y equals square root of x. So, let's see. So y equals x squared we know is parabola, right? And then y equals square root of x is just going to be this function right here. And, we don't really care about the other side of the parabola because the square root function starts on the right side of the plane. So forget about that. So this is the square root of x right here. And on bottom, this is y equals x squared. And we're interested in this region right here. This is our plate. This is green. Now we got to set up our integral. All right, so remember that density is equal to mass over area. and therefore the mass is equal to the density times the area. So we want to, since the density is constant here, but the area is not. So we want to set up an integral. So let's go ahead and do that. Excuse me. The first thing we need to figure out is where these curves intersect to set up my bounds of the integral, right? I'm going to integrate this thing. Now the density function, the density is constant, so I'm just going to pull it outside, and it actually gives it to us. They tell us it's 2 grams per centimeter squared. So I'm going to just pull out that 2 on the outside, and then I'm going to multiply by the area of this region. Well, what's the area of this region, right? So the area is going to be the top curve minus the bottom curve. Right, so this guy minus this height is going to give us the height of our rectangle. Okay, dx. All right, so there's our integral. Now we need to figure out the bounds. So to figure out the bounds, we can just set the two functions equal to each other to see where they intersect. So we have square root of x equals x squared. If I square both sides, I get x is equal to x to the 4th, and then I can subtract x from both sides to get x to the 4th minus x equals 0. Factoring out an x, get x to the 3rd minus 1. And then finally setting each of these things equal to 0, I get x equals 0, x to the 3rd minus 1 equals 0, so x equals 1. So these 2 points are going to be my bounds. These are my points of intersection. So right here, this is my starting at x equals 0, and then my ending is right here at x equals 1. Okay, so those are my bounds for the integral here. And now we can evaluate this thing. So let's go ahead and do that. Clear some of this off. Okay. So the square root of x is the same thing as x to the 1/2. So I'll write that there, and then I'll just find my antiderivative of this function. So antiderivative of x to the 1/2, if I add 1, it's going to be x to 3/2 divided by 3/2 is the same thing as multiplying by 2/3. And then we have minus x to the 3/3, and we're going from 0 to 1. So if I plug in 1, I just get 2/3 minus 1/3. And then again, minus 0, that's all going to clear out. So then I can simplify this to just give me a final answer of 2/3 grams. So this is my mass of this plate that's bounded by square root of x and x squared. All right. Let's do another example. I believe you have an example pretty similar to this on your homework. So we want to find the mass of the triangular region, which has density delta x equals 3 plus x grams per centimeter squared. So this time our density of this thing is not constant. It's going to be increasing as we move along. So, the most density is going to be concentrated over at the end here, or at the right part of this picture. Okay. All right. So how do we do this? Well, we do it the same way that we did the other one. All right, so we have a two-dimensional object. Density equals mass over area. Therefore, mass is equal to density times area. We know that the density function is 3 plus x, so that part's figured out. Now we need to figure out what the area of this region is. How we can set up an integral here. So the first thing we can do is we can recognize that we have two different functions, right, that are intersecting the x-axis. This is our first function right here in red, and the other one is right here in green. Okay, so we need to first figure out what those functions are, and then figure out what the area is by setting up. Basically, we have to set up two different integrals because we have two different functions here. So the first one, if we look, it's a line, right? And we can see that the y-intercept of that line is 3. It intersects the y-axis there. And the slope, well, there's a couple different ways to do this, but I always like the rise over run way. If we rise from the x-axis, we're rising 3, and we're running 1 to get to that next point. I'm sorry. We're running 3 as well, not running 1. I didn't mean that. So this is plus 3 plus 3, which is going to give us a slope of 1. Okay, so our line right here is going to be y equals 1x plus 3. It's just the equation of the line. Y equals mx plus b. Just plugging in m and b. And the equation for the other line is going to be y equals negative x plus 3. Right? Here we're rising 3, but this time we're running to the left 3. So we indicate that running to the left with a negative. Anyway, so y equals negative x plus 3. Okay, so okay. All right, so we're going to split this integral up again because we have these two different functions. So the first integral I'm going to set up is going from x equals negative 3 to x equals 0. And to find the mass, again, I'm just doing density times the area. So I'm going from negative 3 to 0 of the density, which is 3 plus x, times the area. Well, the area is the height times dx, the height of the little rectangles. And we can see here that the height is x plus 3. So this is going to be x plus 3 dx. So that's our first integral. And then the second one, so basically we're going to integrate these guys and add them up to find the total mass. So the second one, we are starting this time at x equals 0. We're starting at x equals 0. We're ending at x equals 3. And we're doing the density, which again is 3 plus x, times the area. Well, this time the area, the height is going to be negative x plus 3. And the width is dx. All right, so let's go ahead and do this. Okay, so let's do the first one. So here, if we FOIL this thing out, this is going to be negative 3 to 0, and then we get first 3 times x. Outer is 9, inner is x squared, and last is 3x. Just expanding that guy. Then combining like terms, we get x squared plus 6x plus 9. So let me rewrite that. X squared plus 6x plus 9. Okay. All right, so finding the antiderivative of this function, I get x to the 3 over 3 plus 6x squared over 2 plus 9x, and I'm going from -3 to 0. So first of all, if I plug in 0 into all of that goes to 0. So I have 0 minus, and then if I plug in -3 in for x, I get something ugly. Let's see what it is. Okay. So let's get out the calculator and see what we get here. Okay. So here I get 9. So this is 9 grams. So that's the mass of this first part. Now let's go ahead and figure out the second integral. So for the second part, I'm going from 0 to 3. And if I FOIL this thing, let's see. I get -3x plus 9 minus x squared plus 3x. So these guys are going to cancel, and I'm just left with 9 minus x squared dx. Okay, so let's go ahead and find the antiderivative of this. Here we get 9x minus x to the 3 over 3. I'm going from 0 to 3. And here I get 27 minus 27 over 3. So it's going to be 27 minus 9, which is going to give me 18 grams. Okay, so adding up these two, so 9 grams plus 18 grams, my total answer, my final answer is going to be 27 grams. So that is the mass of this entire plate from -3 to 3. Okay, all right, let's bump it up once again, another dimension. So we want to find the mass of a hemisphere with radius 7 feet and constant density, and the density is 2 grams per feet cubed. Okay, so now we have a hemisphere. So maybe it looks something like this. All right, and the radius of this thing is given as 7 feet. All right, so let's keep in mind the density formula for three-dimensional objects. The density for a three-dimensional object is going to be the mass divided by the volume. Okay, so here, if we multiply both sides by the volume, we get that the mass is equal to density times the volume. Well, we can see that the volume is the volume of the little discs are changing, right? This is kind of like what we did a few weeks ago, right? So the mass is going to be the density times the volume. Well, what's the volume of this hemisphere? That's what we want to know. What's the volume? Well, just like we did a few weeks ago, we can figure that out pretty easily, right? The volume of the hemisphere is going to be the sum of the volume of these little cylinders, right? Remember this? Remember we had some thickness here. So we had some thickness of, let's say, I don't know, dH, the thickness of the cylinder. And then we had to figure out what the radius of the cylinder was in terms of h. You guys remember that? So that's what we're going to have to do here. If we take a cross section of this thing, what we want to do, remember that the volume, we're going from, first of all, the radius of the hemisphere is 7. So if we are integrating with respect to the height, we're going from 0 to 7 feet. Right, so the volume of this thing, we're going from 0 to 7 feet. And then we have pi r squared times dH. Right? So that was the volume. And then, of course, we have to multiply by density to figure out what the mass is. So the density is constant, so that can come out in the front. So this is the mass. Okay? Now, remember what we had to do. We had to turn R in terms of H since we are integrating with respect to H. And to do that, we did a little trick. Let's say that we have a disk at height H. And we want to figure out, what is this radius right here? Well, we know that since we have a hemisphere, if I draw a line from the center to the edge, that's going to be the radius. So the radius was 7. And so the trick is that we can get R in terms of H with Pythagorean theorem. So we have leg squared plus leg squared equals hypotenuse squared. So we have h squared plus r squared equals 49. And if I solve for r, I'll subtract h squared from both sides. And finally, I'll square root both sides to get r is equal to the square root of 49 minus h squared. So that's what I can plug in right here. Okay, so I have that the mass is equal to 2 from 0 to 7 pi times r, which is square root of 49 minus h squared dh. Okay, so far so good. So the nice thing here is that the square root and the square they're going to undo each other. And what we're left with, I'll write it over here, is 2 from 0 to 7. And actually, I'll pull out the pi too. Let's pull out the pi, since that's a constant. Then I have 49 minus h squared dh. So integrating this thing with respect to h, I get 2 pi on the outside, 49h minus h to the 3 over 3, and I'm going from 0 to 7. Okay. So what this ends up being when I plug in 7 for h is I get 1,436.8 grams. So that is going to be the mass of this hemisphere right here, and it has constant density. So in Calc 3, we're going to do more problems like this, but we are going to, for the three-dimensional objects, we're going to have non-constant density, and that we can use what are called double integrals to to find that. So yeah. So anyway, okay. So that's what we did. So we did this in the three-dimensional case. Very nice. Okay, so we just talked about mass using density and volume, density and area in the 2D case, and density and length in the 1D case. So the next topic I'm going to talk about in this lecture is center of mass. So basically that is the point that balances something. So you can imagine, if you have like a, if you have like just a rock, just a uniform rock of uniform density, and you try to balance it. Well, if it's uniform density, the balancing point is going to be directly in the middle, okay, for anything that has uniform density. But if something doesn't have uniform density, like for instance, if this was heavier on this side, the center of mass is going to shift. Okay, you're going to have to put that pencil more to the left if it's heavier on the left side. So that's what we're looking at, okay? So the question that I have here is how do we balance the seesaw? And we have two children on this seesaw. One is pretty hefty, 200 pounds, and the other one is 100 pounds. This child is 7 feet away from the center, the pivot point, and this child is 8 feet away. And so, as you can probably guess, the seesaw is going to tip more to the left with this heavier child 7 feet away from the pivot point. And the question is, where do I have to put that pivot point so that the seesaw is level? That's what we're going to investigate here. Okay, so we need to find the center of mass to balance the seesaw so we can move the pivot. Okay, so here's a definition that we need to know before we start with the center of mass business. A moment, okay? So basically what a moment is a tendency, in this case, for the child to turn the seesaw system about the pivot point. And the equation is the mass times the displacement. So let's calculate these children's moments. Basically the tendency to turn the seesaw in their direction. All right, so the first thing I'm going to do is I'm going to say that this is at the point x equals 0, okay? Now, notice that the bigger child, the hefty one, is to the left of x equals 0, and he's 7 feet away from it. So I'm going to call his displacement -7. That's what displacement is. It's just length with direction. So he is, oops, I don't know why that disappeared there. Let's see. That was weird. Let me draw that again. So this bigger child is, let's say the moment of the bigger child is equal to the mass, which is 200 pounds, times the displacement, which is -7. So the moment is going to be -1400. Okay, so this is and maybe I'll actually just write it out here. The moment, just so it doesn't get confused with mass. All right, so this is the moment of the bigger child. Calculating the moment of the smaller child, we have moment of the smaller child is going to be equal to his mass, which is 100 pounds, times the displacement. This time he is to the right of the pivot point, the little fulcrum there. So this is going to be times 800. Or sorry, times 8. And that's going to give us a moment of 800. And so you can kind of like compare these and say, well, who wins? Who has the bigger magnitude here? And that's going to be the moment of the bigger child, 1400. And so that's telling us that the seesaw is going to go down. It's going to tend in his direction. And the question is, how do we get this thing balanced? Well, it's going to stay balanced if the moments sum up to 0, right? It's going to stay balanced. Let's see. Yeah, so in order for the seesaw to stay balanced, we need the sum of the children's moments to equal 0. And that's where the center of mass comes in. The center of mass tells us where to move that pivot point so that the children's moments sum to 0. And this is the formula for the center of mass. So we take the mass of the first child times the displacement of the first child plus the mass of the second child times the displacement of the second child all over the total mass. So let's actually calculate this. So let's calculate where the center of mass is. So m1 times d1, so the mass of the first is going to be, it's going to be 200 times the displacement, which we said was -7. So the center of mass is equal to 200 times -7 plus mass of the second child is 100 times the displacement. Is going to be 8 feet away, all divided by the total mass. So 200 plus 100. So the center of mass, if we simplify the top, we're going to get -600 over 300. And so the center of mass is going to be at -2. All right. So that's where we need to shift the pivot point to get this thing balanced. 2 units to where it was. So keep in mind where it is currently without shifting it is at x equals 0. If we shift that thing over 2 units to the left, now everything's balanced. And here's it shifted. Here's my hefty guy over here, 200 pounds. And now he's not 7 feet away. The thing shifted 2 units his way, so now he's only 5 feet away. But this guy, this 100-pound guy, well, it moved to the left 2 units. So he's not 8 feet away anymore. He's actually 8 plus 2 feet away, 10 feet. He's 10 feet away. So this is the point right here. This is -2. This is the center of mass. And let's verify that this indeed is the center of mass. Remember, if the sum of the moments of the children equals 0, then the center of mass is, or the pivot point is in the right spot. So the sum of the moments we have, again, mass times displacement. This time we have 200 mass times displacement. This time it's -5, right? Plus mass is 100 pounds times displacement. This time it's 10. And we can see that we get -1,000 plus 1,000 is equal to 0. So yes, the sum of the moments equals 0, and the seesaw is indeed balanced. Okay, so what we just talked about, the kids on the seesaw, those are called point masses. Okay, so the center of mass of a system of n point masses located at positions x1, x2, all the way to xn along the x-axis is given by this formula. And basically, we use x bar to indicate the center of mass. And all this is saying is the sum of the moments, this is on top, right? We're taking displacement times the mass and we're adding them all up, however many things are in our system. With our seesaw, we only had 2 people in our system, so our formula looks like this. But if we had more than 2 people, we would just keep adding on, like plus M3, D3, plus M4, D4, etc. So that's what the top means. And the bottom is just the sum of the masses, just like we did in the seesaw example. But this is just saying, we could have more than 2 masses. We could have n masses, whatever n could be. N could be any finite number. All right, so let's do some examples here. Find the center of mass of a system containing 3 point masses of 8 grams, 3 grams, and 1 gram located at the points x equals -3, x equals 0, and x equals 4. Okay, so remember we have the center of mass is going to be the sum of the moments, which is mass times displacement, over the sum of the masses. So if we were to draw these things, here we have our number line, here we have x equals -3, and we have x equals 0, and x equals 4. And then we have our masses here. So 8 grams is going to be at -3, so this is 8 grams. And we have 3 grams at 0. It's probably not drawn to scale, but it's okay. And then at x equals 4, we have 1 gram. So what can we expect here? Well, the center of mass is going to tend towards the more heavy object. So we expect the center of mass to be in this region, right? That's what we're expecting. So let's actually do the calculation now. So the calculation, the center of mass is going to be the sum of the moments. So the first moment we have mass times displacement, so 8 times -3. The second moment is going to be mass times displacement, so 3 times 0, plus the third moment is going to be mass times displacement, which is 4. And then we're going to divide this by the total mass. So 8 plus 3 plus 1. And what we end up getting here is -5/3, which indeed is within this region. Okay, so that's where we have to put the pivot point so that the system stays balanced. So -5/3 is our answer there. All right, so we just talked about point masses arranged along the x-axis. What if we have an object that's lying on the x-axis between x equals a and x equals b? Well, then the center of mass equation becomes an equation that involves integrals. So the center of mass is going to be the integral from a to b of x times the density function all over the integral of a to b density function. Okay, so where are these values coming from, right? So here, the density is mass per unit length. Okay, so we are working in a one-dimensional case here. So remember, the center of mass was the sum of the moments divided by the sum of the masses. And that's exactly what we have here for a continuous object, right? We have this guy represents our our displacement, and the integral of, remember we said this in the one-dimensional case, that when we integrate density, this is representing the mass when we integrate density. And this guy is representing the displacement. So moments, displacement times mass, the sum of these. So that's how we're getting this top part. Now, if we consider the bottom part, well, that is just the mass, right? When I integrate the density function, that is going to give us the mass in one dimension. So that's where the sum of the masses comes from in this bottom, the bottom part. All right, so let's actually do some examples here. It says, find the center of mass of a 2-meter rod. Again, rod, we're thinking one dimension, lying on the x-axis with its left end at the origin if, first of all, A, the density is constant and the total mass is 5 kilograms, and B, the density is represented by the function delta x equals 15x squared. So let's go ahead and tackle A first. So here the density is constant, which is good. So remember, we just had this formula. If it's lying on the x-axis, we're going from A to B of the density function. Well, actually, I wrote it backwards, but it doesn't matter. X times the density function dx and divided by A to B, the density function dx. Okay? So, the first thing is, they tell us the density is constant. Now, we are in the one-dimensional case. We're dealing with a rod lying on the x-axis. So we have this formula, density is equal to mass over length. Okay? So, what is the length in this case of the rod? Well, the length is 2 meters, right? And so L is equal to 2. And we don't know what the density is. But what we do know is that the mass is 5 kilograms, all right? So using this formula, we have that the density is equal to 5 over 2. So that's our constant density. Okay? So let's go ahead and replace that in here with 5 over 2. Now, since they tell us the total mass, we don't have to do the extra work to integrate. We can just say, well, the total mass is going to be this bottom portion, and we were told that it's 5. So this is what we have so far for part A. Let's go ahead and pull out the 5 over 2. So we have 5 over 2 x dx over 5. And what are our limits of integration? Well, it says that the rod is lying on the x-axis with its left point at the origin, and it's going all the way out until 2 meters, right? It's a 2-meter rod. So we're going from x equals 0. We're going from x equals 0 to x equals 2. So let's go ahead and figure out what this is. We get 5 halves. Antiderivative of x is x squared over 2. We're going from 0 to 2. And this is all over 5. Okay? So we have 5 halves. 2 squared is 4. 4 divided by 2 is 2. And so we end up getting 1 meter. So 1 meter, that is our center of mass. Now, does this make sense? Does this make sense intuitively? Well, I think so, because remember, we were told that this thing has constant density all the way throughout. So when that's the case, the center of mass is in the middle of the object. Well, we started at x equals 0, and the middle of this thing is going to be x equals 1 meter. So this does make sense intuitively to me. Now let's take a look at part B. Part B is, we're told that the density is going to be delta x equals 15x squared. So this time we need to set up our integral a little bit differently because this density is not uniform, or it's not constant. So let's look at that. So for part B, let's go ahead and set up our integral here. So part B, we have the center of mass. Well, again, we're going from 0 to 2, no change there. And then we're going to take the density function and multiply it by the displacement. So we have x times and this is all going to be over the mass. So we're going from okay. So the density function is 15x squared, so we can go ahead and plug that in. So we have, going from 0 to 2, x times 15x squared dx over 0 to 2, 15x squared dx. Okay, so what I can do first of all is I can pull out the 15 and on the top and the bottom. And when I do that, I'm left with x to the 3 dx over 15 x squared dx. And let me just go ahead and integrate these guys. Now the 15s cancel, that's pretty nice. So on top, I get x to the 4 over 4 from 0 to 2. And on bottom, I get x to the 3 over 3 from 0 to 2. So I end up getting 2 to the 4th, 16 over 4 is 4, divided by 2 to the 3rd is 8 over 3. And when I simplify that, I just get 3 over 2 meters. Okay, so that's where our center of mass is now, that we no longer have constant density. The density, as we can see, is increasing as x increases. So it does make sense that I have to now move my pivot point. I have to move my pencil or whatever you're trying to balance this imaginary rod on from the very center to right here at 3/2, which is 1.5. Okay, so that's where our center of mass is going to be now. Okay, so let's talk about finding the center of mass in the two-dimensional case. So here I have this region that is bounded by the curves y equals f of x in orange and the curve y equals g of x in green. Okay, so since we are now in the two-dimensional case talking about center of mass, we need to remember our two-dimensional density formula. So the density formula, again, in the two-dimensional case, is mass over area. All right, so total mass is going to be the density times the area of that region. Now, let's go ahead and talk about let's remind ourselves about, the mass of this region by looking at the individual little rectangles that I've drawn. So the mass of each of these rectangles is going to be the density, which is this delta x, times the area, which is going to be the f of x minus g of x times delta x. And again, the f minus g is just the height of the rectangle, right? So that was the mass of the strip, and we kind of talked about that a little bit already a couple of slides ago. But let's talk about the center of mass of each of these little strips. So here's the idea. The idea is that these strips are so thin that the density is constant, right? The strips are so thin that the density is constant. And so with that being said, because the density is constant, because we have such small strips, then the center of mass is going to be exactly in the middle of that strip, okay? So what does exactly in the middle mean? Well, I've indicated that with these little red dots, okay? The center of mass of each of these little strips is going to be the x-coordinate, right? That's located at the x-coordinate. So that's our first coordinate of the center of mass. And then the second coordinate is the y-coordinate. So it's the average of the heights of f of x plus g of x, right? It's going to be this guy plus this guy divided by 2, which is going to give us that middle point, okay? And I'm just kind of showing you this to give you some intuition. I mean, I'm going to give you the formulas, but I just kind of want to show you where this is coming from because I think it's super cool. All right, so with that being said, we need to talk about, because we have a two-dimensional object, now we're going to have two components of the center of mass. We're going to have an x component and we're going to have a y component. And before we talk about that, we need to talk about what m sub y is, the moment about the y-axis. So remember, moment is just displacement times mass, okay? So in our case, the moment about the y-axis, well, what's the displacement from the y-axis? What is the displacement from the y-axis? Well, that's just going to be, if we look at any of these rectangles, that's just going to be x, right? That's the displacement from the y-axis. We can see that that's where this is coming from, okay? Times the density function times the area. So that is going to be our moment about y. Okay, great. Now the moment about x is going to look a little bit different, right? So this time, the question that you should ask yourself is, what is the displacement from the center of that rectangle to the x-axis? Well, it's not going to be y, right? It's not going to just be y. It's going to be the average of the y's. It's going to be f of x plus g of x divided by 2. And that's where we're getting this component from. This is the displacement from the x-axis. All right, so that's that. Then we have, of course, the density. So this is the displacement. This is the displacement times the density times the area. All right, so that is going to be our moment about the x-axis. And we can simplify this by foiling f plus g times f minus g to give us this formula right here. All right, so hopefully this picture kind of gives you some intuition of where we're getting these values from. But from this point on, you guys are just going to have to use the formulas. You're not going to have to derive anything or do that. So let's scroll down here. To find the coordinates for the center of mass, we find the center of mass along the x direction as well as the center of mass along the y direction. And it might be a little confusing because we see x matched with y over here, and then we see y matched with x over here. But remember that the center of mass for x, well, again, this moment is measured from the y-axis, and that's the x value. So that's kind of how those two coincide. I know it might be a little confusing, but I think you guys might get the hang of it once we do some examples. So let's just do that then. Putting this all together, we have our formulas for the x-coordinate of the center of mass and the y-coordinate of the center of mass. So let's go ahead and do some examples. We want to find the center of mass of the region bounded by square root of x and x squared, and it says the density of the region is constant, which is cool. That's going to be good. So what are we expecting with a constant density? Well, we're expecting that the center of mass is, in the middle, basically, of these two functions of this region. So let's go ahead and sketch our picture for these curves. So first of all, we have square root of x. That's going to be something like this. And then we have y equals x squared, something like this. And so our job right now is to figure out where they intersect so we can set up our integrals appropriately. And from there, we're going to figure out where we need to put the center of mass. Okay, so let's look at the intersection first. We need to figure out where they intersect, so we take the functions and set them equal to each other and solve for x. So if I square both sides, I get x equals x to the fourth. Subtracting x from both sides, I get x to the fourth minus x equals 0. Finally, factoring out an x, we get x to the third minus 1. And setting these factors to 0, we get x equals 0 and x to the 3 minus 1 equals 0. So x to the 3 equals 1, so x equals 1. Okay, so these are the points of intersection. So those are going to be our bounds for our integrals. Okay, so this is 0, x equals 0, and this is x equals 1 at that upper bound. Okay, so what we have is the integral from 0 to 1, just following our formula, x. Now, the density is constant, so I'm just, instead of putting delta x, I'm just going to put delta there, times f of x minus g of x. Well, f of x is our top function, which is square root of x, and g of x is our bottom function, which is x squared. So we have square root of x minus x squared dx. Okay? And that is going to all be over the mass. Well, remember, the mass in the two-dimensional case is simply the integral from 0 to 1 of the density times the area, right? And the area of this region, we just said, was square root of x minus x squared dx. Okay, so that is our mass on the bottom. Okay, cool. So let's go ahead and figure this out now. Now what's cool is that the density is constant, so the first thing I can do is I can pull out the density in both of these integrals. And when I do that, they're going to cancel out. So let's go ahead and get that over with. So these guys are going to cancel. Very nice. And I can distribute that x up there to clean this up a little bit. So x to the first times x to the 1/2 is going to be x to the 3/2 minus x to the third, just distributing. And on bottom, I'm just going to rewrite square root as x to the 1/2. Okay, so far so good. Okay, so now what I need to do is I need to go ahead and find the antiderivatives. So, excuse me. So x to the 3 halves, if I add 1, I get x to the 5 halves over 5 halves is the same thing as times 2/5 minus x to the 4 over 4. We're going from 0 to 1 on top. And then on bottom, I get x to the 3 halves over 3 halves, which is the same thing as 2 over 3 times, minus x to the 3 over 3 from 0 to 1. Okay, so if I plug in 1 into the top function, I get, 2/5 minus a fourth. 2/5 minus a fourth on top. And again, this is x bar. 2/5 minus a fourth over, on bottom, I get 2/3 minus a third. And when I simplify this, I get 9 over 20. Okay, so that is the x component of my center of mass. Now, since this is a two-dimensional object, we don't just need an x component. We also need a y component. All right, so here is 9 over 20 is going to be a little less than halfway. So this is going to be 9 over 20. So we know that's the x component of our center of mass. And let's go ahead and figure out what the y component is now. Let's see. Okay. Okay, so the bottom is going to stay the same. It's just the mass. The top, remember, we're going to have, it's going to be a little bit different. We're going to have a half times delta. We're not doing the x because it's a constant density. And then we have f of x squared minus g of x squared dx. Okay, so then, again, we can pull those densities out in the front, and they're basically going to cancel. And actually, I can pull out the 1/2 on the top as well. So let's do that. And f of x, we said, was square root of x. So this is going to be the square root of x squared minus, and then we have x squared squared, which is x to the 4th. So just plugging in our values here. Now the bottom, we already found in the previous problem, so I'm just going to basically copy it down here. In the previous problem, the bottom was 1/3 when we evaluated that integral. So I'm just going to put it down here just to save some time here because we already did that. Okay, so now what's cool is the square root and the square are going to cancel each other out on top. And we get this. We get x minus x to the 4th dx over 1 over 3. So finding the antiderivative up top, I get x squared over 2 minus x to the 5 over 5, and we're going from 0 to 1. And let's go ahead and figure out what this is. So y bar is going to be 1/2. Then we have 1 over 2 minus 1/5 minus 0. Kind of just ignore that. Over 1 over 3. And so again, for y bar, we're getting 9 over 20. So this is y bar. This is the y component of the center of mass. So on our picture right here, well, let's see. So we have x is 9 over 20 and y is also 9 over 20. So it looks like our center of mass is about right here. So this is the point 9 over 20, 9 over 20. This is x bar, y bar. Okay, let's do another example. Find x bar and y bar of the region bounded by y equals x squared and y equals 8 minus x squared. The density is constant again. Okay, so let's draw our picture first. we have two functions. We have a parabola, y equals x squared. And then we have an upside down parabola, y equals 8 minus x squared. So maybe something like this. And we want to figure out the center of mass of this region. Now, it looks like this, well, it is, this region is symmetric about the y-axis, right? I mean, you can see that this side and this side are perfectly equal. And so what we're expecting here is that the x value of the center of mass is going to be 0, right? So let's go ahead and figure out what this is. Okay, so all right, so actually, and let me just label some points. So maybe this is gonna make things a little bit more clear down the road. So this is 0, 0. Okay, so there's some points. Now we need to figure out what our integral is. So we need to figure out what these points of intersection are to set up our limits. And we do that by setting these things equal to each other and solving. We have x squared equals 8 minus x squared. And if I add x squared to both sides, I get 2x squared equals 8. Dividing both sides by 2, I get x squared equals 4. And finally, taking the square root of 4, I get x is equal to positive and minus 2. Okay, so these are my points of intersection. And so those are my my bounds for my integral. So let's set this up. So let's look at x bar first. Now we're pretty confident that it's 0, but let's do the math and just make sure it adds up. Okay, so what do we have here is we're going from 0 to 1, right? And then we have x times a density function, but it's not a function, it's constant. Well, it's a constant function. F of x minus g of x. So we have top function, 8 minus x squared, minus bottom function, which is x squared, dx, all over the mass, okay? So the mass, again, is just going to be from 0 to 1 of the density times the area, which area under the curve, we're going from 8 minus x squared minus x squared dx. Okay. Very nice, very nice. And actually, I don't know why I put these integrals bounds as 0 to 1. They should be negative 2 to 2. I'm tripping. Okay, let's see. Let's fix that. So negative 2 to 2. Okay. All right, first things first, I'm going to pull out the density because it's constant. So I'm going to pull that out, and I'm not going to show this step, but they're going to cancel once they're pulled outside of the integral. So, so those cancel out, and I'm also going to combine like terms. So on the top, I have 8 minus 2x squared times x dx. And on bottom, again, I'm just left with 8 minus 2x squared dx. Okay, so let's go ahead and figure this out. So on top, if I distribute that x in, I get 8x minus 2x to the third. Let's see. Okay, so finding the antiderivative, and again, this is x bar. Finding the antiderivative, I get 8x squared over 2 minus 2x to the 4 over 4. We're going from negative 2 to 2. This is on top. And on bottom, I get 8x minus 2x to the 3 over 3, again, from negative 2 to 2. So let's go ahead and figure out what this is. So x bar is equal to, well, I can simplify the top a little bit. 8 over 2 is 4. this is going to be 4x squared. I'll write that like that. And then 2 over 4 is just 1 over 2, so this is 1 over 2 x to the 4. Just cleaning that up a little bit. Okay, so now if I plug in 2 for x on top, so that's our first part, minus, now we have to plug in negative 2. So 4 times negative 2 squared minus 1/2 times negative 2 to the 4th. Okay. And on bottom, plugging in 2 first, I get 8 times 2 minus 2 to the 2 over 3 minus, now we need to plug in negative 2 by the fundamental theorem of calculus, minus 2 times negative 2 to the 3rd over 3. Okay, so let's clean up this mess. Okay, so on top, it looks like I have, let's see, I have 8 minus 1/2 times 16 is 8. So that's 0, right? Yeah. Wait, no, I didn't do that. 16. See, I'm tripping. Nope. Okay, let's see. So this is 4 times 4. Okay, that's 16 minus, and then we have 1/2 times 16. So 16 minus 8. Okay, so that's our first part. Minus, and then negative 2 squared is again positive 4. So this is just going to be 4 times 4 is 16. And then again, we have 1/2 of 16, because this is even, which is 8. Okay, so we get 0 on top, which we expected. And then, so this is going to be 0 on top. And then on the bottom, just to have this for later, we get, let's see, 16, and then 2 times 8 is 16 over 3, so we have 16 minus 16 thirds. Great. Minus, and then we have negative 16. Negative 8 times negative 2 is a positive 16 thirds. So on the bottom, it looks like we get, let's see, 16 plus 16 is 32. Negative 16 over 3 minus 16 over 3, that's negative 32 thirds. So on bottom, and I'm doing this because this is going to help us with our y bar calculation. So 32 minus 32 thirds is 64 thirds on bottom. All right. So 0 over anything is 0, so x bar is 0 as we expected. So x bar is 0. Very nice. Let's keep that in our heads up here. X bar is 0. Now let's go ahead and figure out what y bar is. And remembering that 64 thirds, because that's going to be the denominator. That's our mass. Okay, so let's see. 64 thirds. Okay, doing our y bar calculation now. Okay, so y bar, again, we're going from negative 2 to 2. We have 1/2 times the density times top function squared minus bottom function squared dx, all divided by the mass, which is negative 2 to 2, density times area, which was x squared minus 8 minus x squared. I think I did that right. I'm like looking at the calculations to see if we... Okay. Well, I think that's good. Okay. All right. So we said that the bottom was 64 over 3. That's what I'm going to do. I'm going to factor out this guy, get rid of it. And then the bottom, we just found the bottom before. It's 64 over 3. So I'm going to just replace the bottom with that just to give us some more breathing room here. Okay. All right. Great. I'm going to pull out the 1/2. Negative 2 to 2. And then I'm going to simplify the inside a little bit. X squared squared is x to the 4 minus, then I have 8 minus x squared squared. So let's FOIL this out. 8 minus x squared squared is 8 minus x squared times itself. So first, outer, inner, last. So this is 64. Sorry, guys. 64 minus 16x squared plus x to the 4. Okay? So this is going to be 64 minus 16x squared plus x to the 4. Okay? Okay, good. So let's see. Oh, I think I might have done this backwards. I did bottom minus top. Oh, okay. Sorry, guys. Technical glitch here. Let's flip it. So I did bottom minus top, but we need to do top minus bottom. So this is that minus x to the 4th. All right, great. Okay, so let's get rid of this. So 8 minus x squared squared, we just have x to the 4th minus 16x squared plus 64 minus x to the 4th. That's nice. Those x to the 4ths are going to cancel. And let me just double check this. One wrong move could be fatal. So let's see. We got 64. Okay. Okay. 64 minus... Yeah, that looks good. Okay, so these x to the 4s are going to cancel. And we're just left with this over over 64 thirds. Okay. All right, so let's go ahead and compute this antiderivative. Negative 16x squared, this becomes negative 16x to the 3 over 3 plus 64x, and we're going from negative 2 to 2, and all of this is over 64 thirds. Okay, so on top, I'm not going to do all of this because I feel like you guys know how to do this by now. Plug it using the fundamental theorem, plugging in 2 and then negative 2 and subtracting. On top, what we end up getting when we do the calculations is 256 over 3. And then on the bottom, again, we have 64 thirds. So this is just going to simplify out to 4. So y bar is equal to 4. Now let's go back up to our picture. So our center of mass is going to be at the point x is 0, y is 4. Maybe I'll do it in purple. This is our center of mass. And that is going to be right here, right smack dab in the center. So, all right, guys, that is that is it for this lecture. Sorry, I'm kind of sick right now, so I sound a little bit weird, but anyway, I hope you guys learned something cool today, and I will see you guys next week. Thanks for watching.